All right, hi guys. Today we are continuing on with some additional mini proofs. And remember, we've been using our theorem page as more or less a menu of different theorems and definitions and properties. Goodness, I was trying to erase. That we can reference to justify our decisions that we make with these proofs. So if we're looking at the first one here, we have a diagram, and our given statement is that line AB is parallel to line CD, right? So those are our two parallel lines. That's our given. And then we are trying to prove that angle AEF, which if I connect those endpoints, this would be angle AEF, is congruent to angle DFE. So we're trying to prove that these two angles are congruent. So if we know that they are parallel, then with respect to one another, if we think back to our unit on angle relationships, these two angles we know are alternate interior. And if I look at my kind of menu of theorems and properties and things of that sort, kind of looking for anything that might pertain to interior angles, look at this right here. I have my alternate interior angles theorem, which tells me that if two lines are parallel, then the alternate interior angles are congruent. So that's what I would use to justify this first one. So I can go ahead and say alternate interior angles theorem to justify. So it's kind of nice when they're just one step. It's really just finding which theorem relates the definition to the thing that we're trying to prove. Okay, second one, similar diagram. I have two parallel lines with a transversal, and I know they're parallel based on the given here, telling me that line AB is parallel to line CD once again. And we're trying to prove that angle 1 is congruent to angle 2. Now again, with respect to one another, those two would be classified as corresponding angles. So if I jump back to my theorems decisions, I have a corresponding angles postulate, which tells me that if two lines are parallel, then their corresponding angles are congruent. So that would be my justification for this guy. I can go ahead and just say the corresponding angles postulate. Corresponding, which this word never looks correct when you spell it out. Corresponding angles postulate. So again, just knowing how those angles relate to each other helps me to find my justification. Okay, next one, we are told that angles G and H are a linear pair. That's my given. So we're told that they form a linear pair, these two guys here. And we're trying to prove that they are supplementary. So when I go to hunt on my theorem sheet, I'm looking for things that pertain to supplementary or linear pair, right? Anything that maybe has those keywords involved. So if I'm kind of hunting through, and sometimes, you know, when you're getting used to just the layout here, you might have to look, flip through a bit before you get your orientation. But here we have the linear pair theorem, which tells me that if a linear pair of angles, well, it's not correct grammar. If there's a linear pair of angles, then they're supplementary. So that's exactly what I'm going to use to prove this here. It's just my linear pair theorem. Linear pair theorem. Not too bad at all. Okay. Next one, we have a diagram here, and that's actually our given. They're not giving us any other statements or things of that sort. So the diagram is just the given, and we're trying to prove that angle 4 is congruent to angle 5. So again, we like to establish, well, what kind of relationship do these two angles have? If they are across from one another, we already have an idea that those should be vertical, right? So I'm going to hunt for anything on this page here that talks about vertical angles and how that might relate to them being congruent. We already have an idea that they should be the same measure, by the way, but we're looking to just formally establish that. And there we have it, vertical angle theorem. If angles 1 and 2 are vertical, then they're congruent. That's exactly what it's saying. So if I jump back here, vertical angle theorem would be my reason. Vertical angle theorem. Cool. All right. Next one, now we're moving into some triangles. So we are told that triangle FGH is isosceles. And remember, based on our definitions of triangles, it's isosceles if we have two congruent sides, and those are called the legs. And we're trying to prove that angle H is congruent to angle F. Now, if we think back to our discussion on isosceles triangles, kind of the I was going to say geography of the makeup here, the anatomy of the triangle has these legs which are across from what are called base angles, right? So let's go ahead and hunt on our sheet for anything that talks about isosceles triangles or base angles. We're just hunting. There we have. If a triangle is isosceles and the base angles are congruent, that's exactly what we were just talking about. So base angle theorem is going to be my reason here. Base angle theorem. Sweet. This next one's pretty similar, except now it's just a diagram and it's not explicitly telling us. But this diagram is exactly the same, right? It's literally an isosceles triangle. And the only difference is that now we just have to gather that from the implicit cues, which is these markings here. So because there are two congruent sides, those are my legs. And so we know, again, just by drawing conclusions from this information given, that those base angles have to be congruent. So even though the given is different, it's still my base angle theorem. So we can use the same justification. It's just a different starting point, right? We have just a diagram to rely on instead of it being explicitly spelled out for us. Okay, now we're getting into some triangle congruence, which we've already been more or less doing proofs with, but now we're just kind of doing it in a different layout, so to speak. So our diagrams are given here. That's what's provided to us. And we're trying to prove that triangle HGF, and let's match up corresponding sides, is congruent to ABC. So HG needs to match with AB. GF needs to match with BC. And FH has to match with CA. Right, so those would be our corresponding, like if I were to actually reorient the two triangles, that's how they would line up. And so if I notice that, well, sure enough, the diagram's telling me that my teal sides are congruent, that my green sides are congruent, and that an included angle is congruent. So we should already be thinking, oh, this is the case of SAS, which is one of my triangle congruence proofs, or theorems, I should say. And so formal name for that, because just to show that these are all listed on your sheet too. It's just a matter of, it's like an Easter egg hunt. There it is. Side angle side postulate, right? That's telling me that if two sides, what is going on with this grammar? If two sides of a triangle are congruent to two sides of a corresponding triangle, and the included angle, oh my goodness, angles are congruent, then the triangles are congruent. So that would be my side angle side postulate. So that's what I'm writing in here. Side angle side postulate. Nice. Or we can abbreviate as SAS. And then let's check out another one. Okay. And again, the diagram is the given. And we are trying to prove that triangle RQS, so let's map out these corresponding sides. RQ, we're trying to prove that's matching with YX. QS would be corresponding to XZ in our proof. And finally, SR would be corresponding to ZY. So once again, I'm being told that my green sides are congruent, that my teal sides are congruent. And notice that there is a corresponding right angle that's congruent as well. But if I'm thinking back to my acronyms, this would be SS, or in the opposite direction, ASS, which is off limits, right? We don't like that, right? So, but there is an exception to this, which is the fact that these are both right triangles means that, oh, we have this HL, hypotenuse leg comparison, that as long as the hypotenuse and one of the legs are corresponding and congruent, then we can use that proof. So if I go back to my theorems, sure enough, my hypotenuse leg theorem is listed. If the leg and hypotenuse of one right triangle is congruent to the corresponding leg and hypotenuse of another, then those two triangles are congruent. So that's what we would use here, is the hypotenuse leg theorem. Hypotenuse leg theorem. Cool. All right, guys, thanks for tuning in to this incredibly riveting presentation, right? Just getting a little more practice with some mini proofs.